Hello, good afternoon, everybody. Am I audible to you, everyone? Please respond, Mama. Hello, CRs. Am I audible or not? You can chat it, Nana. And I wanted to inform you that your unit test exams are cancelled, so it must be postponed to some other day than your October 1st. So the tentative schedule will inform you later. Due to your exams, it is postponed. You already asked this question in the last class, right? So just I confirmed with the coordinator and she said that your unit test exam is cancelled. Okay, this is for your information. Now let me start our class. Today's session is BJT balancing. Am I audible or not? Hello. Okay. Today's session is balancing. Let me move to our topic. The last class we discussed about our configurations of BJT. Three types of configurations: common base, common collector, and common emitter configurations. So, in order to obtain a suitable configuration for amplification, which will act like a perfect amplifier, the common emitter configuration can be utilized as a general amplifier, since its characteristics are all characteristics: input resistance, output resistance, current gain, and voltage gain. All are in the ranges of required ideal characteristics of an amplifier. So in the range of, it is near to that range. So hence we are moving to our session with a common emitter. Now biasing is also described using your common emitter configuration. In order to explain here biasing, how many types of biasing, what does mean by a biasing, what is the importance of biasing in an amplifier. So those are all the things we are going to learn about in today's session. So BJT, bipolar junction transistor biasing. Already you people are known about the PN junction diode biasing. So two types of biasing. If you have one junction, we have forward bias and reverse bias. In a BJT, what is biasing means? Applying a, actually here you're going to utilize here BJT. CR, are you able to listen my voice or not? Am I audible or not? Please respond, Nana. Is there any issue with my audio? Prabha ma'am, am I audible to you, ma'am? Okay, ma'am. Let I continue our class. So today's session we are going to deal about your BJT biasing. So what is the need of biasing that we are going to learn now. So BJT. So in your PNX error we have seen that your PNX error can be forward bias and reverse bias. It can be utilized as a on and off switch, whereas the BJT can be utilized as a amplifier. But out of the three configurations, only the CE configuration is a generalized amplifier because it achieves all the characteristics of an ideal amplifier. So the characteristics or the parameters of a CE configuration is near to that ideal characteristics of an amplifier. So we are preferring the common emitter configuration to describe this biasing topic also. So now simply now let I'm taking a BJT. Now our BJT, so is BJT, if for a BJT, if I'm applying an AC signal, so the voltage strength of this signal must be amplified. So now in order to amplify those signals, so we require a BJT, but without any DC supply it can't amplify your AC signal. So most common application of your transistor is we can use as a amplifier. If we apply a time varying signal as an input signal, and then the BJT without the DC signal it can't amplify. With a DC supply only it amplifies the signal. So this BJT, until you apply the DC power signal, and it has to be and until you apply a proper DC signal, as well as until you apply a proper resistor values of RB and the proper value of your character resistance RC. You can't amplify the signal of AC signal without a biasing. So now what does mean by a biasing? So biasing is nothing but applying a DC signal in order to amplify an AC signal. So a proper biasing of your transistor to amplify an AC signal is known as a biasing. So here what we are going to do is, so we have so many methods to bias your transistor. So out of the five types of biasing techniques, the familiar one is your voltage divider biasing technique. Now coming to this, so your signal which comes out from your amplifier will have some a portion of DC portion and an AC portion. So now why we are need to analyze the DC characteristics? Why we need to analyze the AC characteristics? In order to find the actual, so for a faithful amplification without a distortion of your given analog signal at the output of your transistor, we have to analyze or we have to bias this circuit, and we have to analyze the DC as well as your AC characteristics. So now let I am explaining here what does mean by a biasing. So the definition of your biasing is application of DC voltages which can establish a fixed levels of your current and voltage. So you are taking fixed levels of your collector current as well as the fixed voltage levels of your output voltage. These to obtain that fixed voltage levels and fixed amount of currents, we need to apply a DC signal. So now in a your CE configuration, CV configuration, and CC configuration are utilized for to obtain your characteristics of those configuration, where when I wanted to use your transistor as an amplifier, instead of applying a DC input at the base to emitter junction, we have to base to emitter junction we have to replace with an AC signal. So now if I am applying an AC signal, my output is also in the nature of AC without any distortion. If it doesn't provide the proper biasing, the output is having a distortion. So in order to maintain output, a proper output, a faithful output or a faithful amplification at the output of your amplifier, we require this biasing. So now what about here? Now in order to analyze this DC and AC characteristics, first we have to turn on the transistor into on state. In order to turn on the transistor into on state, there are two techniques we are following in your transistor. One will be the base to emitter junction and collector to base junction of your input junction and output junction of your transistor must be forward biased. So then only the transistor will be in the saturation. So it has to be switched on into on state. But if it is in a saturation state, it can't amplify your signal. So simply a large amount of current is flowing through that, but the voltage levels will not be amplified to that required level based on the current gain. Hence, now we have to operate for a faithful amplification without a distortion. You must operate your transistor under active region. So now the transistor is operated under active region by applying a forward bias at the input junction and a reverse bias in the output junction. So already we are familiar with the input junction and the output junction in a transistor. So emitter to base is your input junction and collector to base junction is your output junction. So now in order to bias that, so your input junction must be forward bias and the output junction, we're going to utilize the DC. So DC supply. So this applied, how much of DC signal you have to apply, how much magnitude of your DC signal you have to apply for a proper biasing, and what are the components that you can connect it to the transistor which can give the faithful amplification of the output, that we have to find it and we have to analyze that using the DC characteristics. Now in order to obtain the DC characteristics and AC characteristics. Let me first take the basic relationships of your in your transistor. As we already discussed in a last class, that emitted current is the summation of its collector current and the base current, where base width is very less, so almost it is negligible. So because in the range of microamp, whereas IC is in the range of microamp, IB is in the range of microamp to nanoamp, whereas IC is in the range of your milliamps. Now the current gain of common emitter. Now I already explained you that we are going to analyze your CE configuration. So in a CE configuration, the beta DC is the current gain. So it is the ratio of output current to input current. Our output current is IC and our input current is IB. Hence IC by IB. So now IE is equal to, if I replace the first equation where it is IC is equal to beta times of IB, then we will have the total amount of emitter current is equal to 1 plus beta times of IB, which is approximately equal to the IC, which is approximately equal to the IC. If I neglect your IB, so approximately I can ignore my IB because it is a very small amount of current. Next, so applying the KVL at the transistor, so in a common emitter configuration, so collector to emitter voltage is the sum of your collector to base and the base to emitter voltage. Now, if I wanted to find the collector to base voltage, then it will be VCE minus VBE. So these are the basic relationships of currents and voltages in a common emitter configuration. Now let I move to your transistor biasing. Now, so here the basic function of your transistor is explained. So in a transistor, the biasing is utilized. So the process of raising your strength of your weak signals without any change in its general shape is referred as a faithful amplification. As I already mentioned, what does mean by faithful? Without distortion. So without a distortion, if we have an output at that amplifier, then it is called as a faithful amplification. So for a faithful amplification, what are the essential criteria we have it? So emitter base junction must be forward bias, collector base junction must be reverse bias, and we should have a proper zero signal collector current, a proper way, because we are not applying any AC signal initially, hence we require a proper zero signal collector current. So for a faithful amplification, we have three criteria to be satisfied in a CE amplifier stage. So input junction must be forward bias and output junction must be reverse bias, as well as if I am not applying any AC signal, so initially will not apply any AC signal, right? So your AC signal will start from the zero amplitude. So we have to maintain a proper zero signal collector current. So these are the three main criteria to obtain a transistor biasing. Next, we'll move to the next slide. So how many types of biasing we have? So now there are majorly we have 5 types of biasing techniques. Out of that 5 types, the familiar one is your self bias. So that is also called as voltage divider bias. So we can also call your self bias biasing technique as a voltage divider biasing technique. So now this is also called as emitter bias, self bias, voltage divider bias. So collect next first one will be your fixed bias, second one will be your collector to base bias. So next third one will be the self bias, fourth one will be your emitter bias, and the fifth one is your base bias with the collector and emitter feedback. So these are the 5 types of biasing. Out of this, the familiar one and let be in our syllabus we have in the voltage divider or self bias. Now, so we'll analyze this self biasing technique. Before we are moving to the self bias, what are the advantages and what are the disadvantages and advantages of your fixed by the other techniques? That also we'll just I'll introduce briefly. So now we'll concentrate on only on the voltage divider bias or the self bias. Now, Next, so these are the output characteristics of a common emitter configuration. Now, in this common emitter configuration, so if I am drawing a line DC, this is called as a the red mark. On the image you have a red mark line, so which denotes a DC load line, and this DC load line indicates the operating point, whereas here we have the nodes on your DC load line which starts from your A to B, and in the midway of your DC load line we have a point called as quiescent point or a operating point. So now, so what is this DC load line? So how to get this DC load line? That are the things we are going to learn now. So now, so we'll understand the biasing. What is the importance of your biasing through the output characteristics of transistor? Is it clear, everybody? Till now, do you have any doubts till this slide? Do you have any doubts? Is it clear, everybody? Respondana? Yours? Is it clear, everybody? Okay, I'll explain you. First, now my voice is clear, right? Why you are not responding? Okay, I'll show that graph. Yes. Now, carefully observe, Nana. So this is we already discussed this in the last class, I think. So output characteristics. What is an output characteristics of a common emitter configuration? This is a curve drawn between your output voltage to the output current. So on your x-axis we are taking VCE, on y-axis we are taking your collector current. In common emitter configuration, our output current is collector current IC and our output voltage is collector to emitter voltage. Hence on x-axis we are taking VCE. So with the variation in the VCE, we have to observe the variation in the collector current for a fixed values of your base current or the input current. So now let me start with IB equal to 0 and we'll vary that IB with a larger values of 25, 50 micrograms, 75, 100, 125 like this. We'll move to up to the fixed values of your IB. So up to the higher ranges of your IB values, and then next. So now this DC load line, how to draw this DC load line is here. Now our common emitter configuration, in order to draw this DC load line, we have to take down the common emitter configuration circuit. Now this is your common emitter configuration circuit, right? In the last class I have explained you the common emitter circuit. So in a common emitter configuration, this is a circuit of your common emitter configuration, and I've explained in the output loop my voltages and currents, how to calculate it, those all the things we have discussed it seems. So here if I am applying the KVL in the output loop, then I can achieve, 1 second. Now, we have a transistor. One second. A transistor which is in common emitter. So we are connecting here, emitter is grounded with a resistor RC. Your VCC is coupled through an resistor RC, through a resistor, collector resistor RC. Your input must be applied in series with your resistance RB. Now, amount of current flow of current, IC collector current, IC, and here the amount of current flow through the emitter terminal is denoted with I. As I already discussed that in your last class. Okay, right. So now if I am applying a KVL at the output loop, so then we would have here VCC, one second, VCC VCC output loop. I'm applying KVL, VCC minus of IC RC minus of collector to emitter voltage is equal to 0. Now amount of collector current IC is equal to VCC minus of VCE divided by RC. Now to obtain this, DC load line, to obtain a DC load line, so in that equation, if I am taking VCE is equal to VCC, then I would have IC is equal to 0. Yes, if VC is equal to VCC, if VC equal to VCC, then I would have IC is equal to 0. Next, so when I have the maximum amount of current, if VC will become 0, then IC must be is equal to VCC divided by RC. So based on that, I am taking two nodes here. One will be the A and another one will be a B. So what are the x coordinate value and y coordinate value on B is, here we see the B coordinate value is, so we have, one second, so y term is, so here we have VCE comma 0, because if my VCE is equal to VCC, VC is equal to VCC, then our collector current become 0. So then I'll get the point B. And whereas at this node, in order to obtain the maximum amount of collector current, so my VCE is 0, x coordinate value is 0. So the coordinate values are, x coordinate value is 0, y coordinate value is become VCC divided by RC. So if I join this node A and node B, that is called as a DC load line. So for a faithful amplification, as we already discussed that Our transistor can act like an amplifier in only active region. Now, look it out here. Now, I'm just crossing this area. So, this belongs to the saturation region. Whereas, the region which is below IB equal to 0 belongs to cutoff region where the collector current is 0. So this belongs to cutoff region and this belongs to active region. Only this portion will be the active region, or we'll also term that as a linear region. So when your transistor is operated on linear region, then only we have the faithful amplification. So your operating point, so for example, now let I am taking a 10 volt VCC or a 9.5, let I am taking. So 9.5 is my VCE value. So that correspondent current will be 2 milliamp. So this is one of the operating point due to the DC signal. So next, another point if I am taking, so your operating point might be on this load line, or it might be here, or it might be here, or it might be here. So and anywhere you can place it. The operating points based on these operating points are based on your applied DC voltages on collector to emitter and collector current, collector to emitter voltage as well as on the collector current. So now if I am having a operating point not on this DC load line, so what happens is, so my signal, AC input signal which I wanted to amplify will superimpose on your operating point. When it is superimposed on operating point, so for example, now my operating point, let I am assuming my operating point is at this position with a VCE of 1 volt and IC of 8.5. Okay, so now this is my DC operating values. So in order to apply the proper biasing, let I apply a VCE of 1 volt, and with that 1 volt of signal, I could have a current IC current with a IB current of 200 microamp is equal to 8.5 milliamp. Now on this one, if I superimpose my inputs AC signal, some part of the signal will be distorted at the output. As we already know that CE configuration will provide your 180 degrees phase shift. For a positive cycle of input, you will get negative cycle. For a negative cycle of input, you will get the positive cycle of output. Now, if I have the operating point at this near to saturation region, then so one part of the signal, for example, like this I have. So now this is my signal. So my positive cycle of my input is distorted and my negative cycle of input is transferred and it is amplified. So a distortion takes place if I place my operating point near to the saturation. Right. I told that so you can put your operating point at anywhere, but why we should put the operating point exactly at the midway of your DC load line is discussed now. So if I am placing at the extreme end of here, or at the near to the saturation region, so then some part of the signal is distorted because one part of the signal is clipped off, only half of the part is transferred, so our output is distorted. So next, let I move to the node N. So node N, so now I choose the operating point at node N. If I choose the operating point at node N, now if I superimpose my AC signal, now I am applying the AC signal, then so only the positive cycle. So here now I am applying my AC signal. Now I'll get now at this node only some part of the signal is amplified. So only positive cycle is allowed, and we at the output will get the negative cycle as and negative cycle if I'm applying, so it may not be properly amplified, and again so we have a distortion. So some part of the negative cycle is distorted. So now so some part now if I am taking below IB equal to 0, I mean to say near to cutoff, exactly at cutoff. So at this node, let I am taking the operating point, and now I'll superimpose my input signal over there. Now almost I have, so there is no amount of current flow in the negative half cycle, hence so amount of current flow, collector current will be 0. If I doesn't have any current at the collector terminal, then the voltage drop, collector to emitter voltage, is also 0. So hence the distorted output will get at the output if my operating so I can't choose the operating point which is near to the saturation or neither to the near to your cutoff region. So for a faithful amplification of your AC signal inputs, so which is having a lower strength, so lower level voltages. So in order to amplify the lower strength signal into a higher levels or to amplify the voltage levels of the signal, so we have to choose the operating point which is exactly at the midway. Then both cycles are amplified with a current gain of beta factor. Current gain of beta factor. So this is the importance of your biasing. What is the need of the biasing in a transistor amplifier circuit? Is it clear, everybody? Is it clear? Yes or no? Okay, right. Can I move to your next slide? If this point is clear, then I'll move to the types of biasing. So now we are taking the predefined DC values on your transistor by applying the proper biasing voltages on input and output junction with the proper components which are placed at the input and at the output. So the values of your RB, RC as well as the VCE, collector current, and the amount of input current IB as well as the amount of input voltages are chosen based on this selection of the operating point. So now so I can also choose the operating point near to the breakdown. So breakdown region, if I choose the operating point at this node end, so already your transistor is driven into breakdown region. If it is driven into so which is not suggestible, so our operating point, it must be placed at the center of your DC load line for the faithful amplification. If you choose that operating point near to the breakdown, so almost at the breakdown, since the transistor is operating in a breakdown region and the operation of the transistor in this region is avoided. So it may damage your transistor. So if you are taking the operating point near to the breakdown region, so heavy amount of current flow in breakdown, so junction breakdown can cause the damage of the transistor with the temperature increase. So hence, so which is not suggestible. So choosing the operating point near to breakdown region or near to saturation and neither to the cutoff region. So hence we have to keep the operating point. So exactly at the DC load line, center of the DC load line. Now, so this DC load line yields the amount of output voltages with corresponding output current. It's nothing but the output voltage for a particular at a time interval. So what is the amount of VCE you are applying in order to obtain a particular amount of current yields to the operating point. Okay, next we'll move to our next slide with the biasings, types of biasings. Now, so this is here one of the type of the biasing technique, fixed bias circuit. So now in this fixed bias circuit, so let I am taking, so now you are applying biasing voltages. You are applying a DC biasing voltage. Now you just see here. So we have two steps to connect the fixed bias circuit. First step is locate your capacitors. So if I wanted to do the DC analysis, then I have to replace those capacitors with the open circuit. This is the first step. Actually, in order to function your transistor as an amplifier, we have to connect the input signal is coupled with a coupling capacitor, as well as to collect your output at the output terminal of your transistor, an AC output signal which is collected from the collector terminal of your transistor. Again we have to connect a coupling capacitor, a coupling element we have to connect it, that will be a capacitor. So C1, C2 are the coupling capacitors. So you are connecting C1 in order to apply the AC input signal, and C2 you are connecting in order to obtain the AC output signal from the collector terminal of your transistor. Done. So first step, first we have to analyze the DC characteristics of this fixed bias circuit. In order to obtain the DC characteristics of this biasing circuit, so let I am just replacing this C1 and C2 with an open circuit. Since in a DC, so if I am having a DC analysis, what is the reactance offered by the capacitor? XC is equal to 1 by 2 pi FC, right? So if for a DC signal, now I am going to analyze my DC analysis. So for the DC analysis, my frequency of DC signal must be 0. So 1 by 0 become infinite. So it offers an infinite resistance for the DC signal. Hence, we have to open circuit here C1, as well as here also C2 must be open circuited to obtain the DC analysis. Next, we have to take the two loops. One will be the input loop and the second one will be the output loop. So now out of these 5 types, we are doing this DC analysis and AC analysis in order to find the best biasing circuit out of the 5. So now let me first started with your fixed bias circuit. So in this fixed bias circuit, what we are going to do is here. So actually in the last session, CE amplifier state, when I am explaining that CE amplifier state, just we applied here VCC through RC and connected to the collector terminal. Now in this fixed bias circuit, we have provided a RB resistor, and that RB resistor is also connected with the same amount of VCC. So now, we are having now 2 loops. One will be the input loop and the other one will be the output loop. So now For analyzation purpose, we'll open the C1, C2. So now let I am just opened here. So just I deleted that capacitors. So C1 and C2, and AC signal input must be also kept to 0. So now we are doing the DC analysis. So AC input signal must be kept to 0. So hence VCC is transferred through RC to the collector terminal, as well as it is also transferred. The supplied signal is also transferred. DC signal is transferred through the RB to the base of your answer, where emitter is grounded. Common emitter configuration it is. So common emitter amplifier, hence emitter is grounded. Now I'm applying. Now next step is here locating your two main loops. One will be the input loop, the other one will be the output loop. This is my input loop and this is my output loop. Now next thing is here, next I have to take the analysis of input by applying your KVL. Now here we have minus VCC or plus VCC. If I am taking here a minus VCC, then it will be plus IBRB. Like I am taking VCC minus of IBRB minus of, like this also you can write it, minus VBE is equal to 0. So from this KVL in the output loop, my base current is equal to VCC minus of VBE divided by RB. VCC minus of VBE divided by RB. As you already know that the input junction or VBE voltage. So VB, the voltage between the base to emitter junction will vary with respect to the temperature. So if temperature increases, then amount of base to emitter junction voltage will reduce by an amount of 2.5 millivolts for every degree raise in temperature of your junction temperature. So your base to emitter junction voltage will reduce with an amount of 2.5 millivolts. So now, so this temperature dependency of VBE must be reduced. But now this IB is depends on RB, which is constant, as well as VCC is also a fixed DC voltage. So now and VB after when you operate your transistor in under active region, and if I properly bias my transistor, so then VB is around, it is 0.7 volts for a silicon, 0.3 volts for a germanium. So until unless the temperature increase, so IB is kept to constant because I have the fixed values of VCC value as well as the RB. Only until unless the temperature increases, so your IB may not change in a fixed bias circuit. If it doesn't change, then it won't affect the output current, collector current IC. So this is a simple circuit. The main advantage of your fixed bias circuit is it's a simple circuit for analyzation as well as to calculate your the stability is also simple. The stability we can obtain with the simple components we require it to construct your fixed bias circuit. Next, let I'm moving to the now the dependency of IC also we have to check that. So in order to find that, we are moving to the output loop. So in output loop, the amount of current flow is from for plus VCC to the ground. So here that I am applying the KVL now. So VCC minus of ICRC minus of VC equal to 0. Hence our collector to emitter voltage or the output voltage is equal to VCC minus of ICRC. As we know that IC is equal to beta times of IB. Now beta times of IB, if I replace IC is equal to beta times of IB. So here if I replace IC with this is VCE, so substituting your A with a B. So equation A is IB is equal to VCC minus of VB divided by RB. VCC minus of VB divided by RB. And you replace this IB with VCC minus VB divided by RB. Now, collector current depends on the current gain. So again, this is one of the factor which can depend on your temperature raise. So the values of this current gain may vary with respect to the increase in the temperature. Whereas now we are taking in output loop, the current flow is from VCC to the ground, where the collector current is IC. Instead of depending on the collector, the amount of current flow through your collector terminal, now it doesn't depend on your RC. Instead of that, it depends on your RV. So it doesn't depends on your RC. Instead of that, here we are making that as with a which depends on your RV. So by choosing the values of your beta DC, so, and RB with a fixed value with fixed resistor value as well as VCC, we can obtain the a perfect quiescent point on the DC load line. So with that we could get the faithful amplification. So it should not move towards your the operating point based on the magnitude of voltages on base to emitter junction or collector to base junction voltage. It should not move into either into if your temperature increases or if your base to emitter voltage changes or if your current gain changes. If it changes, it should not affect the quiescent point. So now the disadvantages is it is unstable because our collector current is dependent on the current gain, where that current gain is also also changes with respect to the temperature. So for the improved stability, what we have to do in a fixed bias circuit is we have to put a emitter resistor. So we have just connected your emitter directly to the common terminal. Instead of that, what we have to do is we have to connect a emitter resistor. Now, and simple circuit it is, but the thing is we used VCC which is applied to the output terminal as well as the same VCC we also applied to the input terminal. Next, we are moving to the next concept or next types of biasing is your voltage divider biasing. Now, in this voltage divider biasing, so what we are going to do is, so with a single DC supply voltage and with a potential divider network, which is comprised by R1 and R2, so we connected that VCC to the base of your transistor common emitter configuration. Now, amount of applied base to emitter voltage depends on the drop across the R2. So which provides the, so this voltage divider bias circuit will provide the highest stability. So quiescent values are maintained exactly at the DC load line, midway of a DC load line. So now we have to use, in order to analyze this DC analysis of voltage divider biasing circuit, we have to use the Thevenin's theorem, and we have to look at the two main loops, where those two main loops are input loop as well as the output loop. Now let I move to that analyzation part. Now this is the circuit after replacing your capacitor, which is now in this circuit. So in your common emitter configuration, we coupled your input Vi is coupled to a coupling capacitor. Now Vi is coupled to a coupling capacitor C1, and we have collected your output using a coupling capacitor C2. But we have to apply the DC analysis, hence we just open circuited that. And not only for why we are coupling this capacitors is, for example, if my AC signal is having a partial DC, and that partial DC again can change the quiescent values of your transistor, so that added DC signal with your input AC signal can disturb the quiescent point of your quiescent values of your transistor. Hence, we are coupling a capacitor at the input loop as well as now. So this is a single stage amplifier of CE. Now, if I wanted to construct a multi-stage amplifier, so then I have to couple my output to a coupling capacitor as an input to the other stage of the other stage of your input of your amp. So then we have the multi-stage amplifier. So in order to nullify the additional DC signal at the output of your amplifier stages, which can disturb the second stage of your multi-stage amplifier quiescent values. So in order to avoid those or to block those additional DC signals of the output of your first stage must not disturb the quiescent values of second stage, we also provided the C2. So now to analyze this circuit, we just open circuited, because for the DC signals it is just simply it is acting like a open circuit and infinite with the infinite resistance. We will treat that as a open circuited element, and Vi is also disconnected because we are doing the DC analyzation part. So Vi is the AC input signal, so we just remove that Vi here, Vi also. Now what is the amount of voltage we are coupling to the base of your transistor, that we have to find it. So in order to obtain that, so let I replace the input loop, this total input loop, with a Thevenin equivalent voltage and in series with a Thevenin resistance. Now that Thevenin resistance is the parallel combination of R1 and R2. So we have R1 into of R2 divided by R1 plus the parallel combination of R1 and R2, because here the voltage is divided, so and that is coupled to the base of your transistor, hence it is named as voltage divider biasing circuit. Right. Now, so RTH is equal to R1 into R2 divided by R1 plus R2. Next, VTH is equal to, what is the amount of coupled voltage to the base of transistor, is equal to voltage drop across here R2. So what is the voltage drop across the R2 is amount of current flow through this path into of R2. So what is the amount of current flow? VCC divided by total resistance is R1 plus, so let I treat that as a I2 into R2. So this R2 is equal to VCC divided by R1 plus R2 into of R2. Hence it is equal to R2 by R1 plus R2 into of VCC. Now I am replacing this total circuit into a equivalent Thevenin equivalent voltage with in series with a Thevenin resistance. Now, so base to emitter junction loop is this, and collector to emitter junction loop is this. So now let me first analyze. Again we are applying the KVL on this. So if I apply the KVL on this, we have VTH minus VTH plus of IB, the amount of current flow through the RTH is base current, hence IB into RTH plus of VBE plus of IE into RE. As IE is equal to beta plus 1. Why it is IE is equal to beta plus 1? Since IE is equal to IC plus IB. where IC is equal to beta times of IB plus of IB. Hence, IE is equal to beta plus 1 times of IB. Now, substituting your IE, so then we could obtain your IB is equal to VTH minus of VBE divided by RTH plus of beta plus 1 into RE. So now the base current of actually your quiescent points or the collector current depends on your IB, right? So that quiescent values, so it depends on the input current IB. Hence we have notated that with a VTH minus of VBE divided by RTH plus beta plus 1 times of RE. Now it depends on your beta, depends on the R1 R2 fixed values. Next depends on the voltage, Thevenin voltage. So and this Thevenin voltage, we recall that Thevenin voltage is equal to, so VCC is fixed value, it may not change because these are also fixed resistor values, so it may not change based on the temperature. Now the stability will be more, the base current, the fixed amount of base current can flow through your junction, which cannot change your collector current. Next, CE loop analysis, output loop analysis we are doing. Now minus VCC plus of ICRC plus VCE plus of IE into I. As we already know that if I ignore your base current, IE is approximately equal to IC. Hence RVCE, just replace this IC with IE with IC, then we have here VCC minus of IC into RC plus RE. So as IB is constant, then IC is also constant. So VC, the fixed quiescent value of VC is also fixed. So with this, we have finished our voltage divider biasing circuits. So most stable biasing circuit is your voltage divider bias, and it is very simple to construct and very simple to we can achieve more stability than your other biasing techniques. So is it clear, everybody? So with this, I wanted to conclude this session. In the next class, we're going to learn about the advantages as well as the disadvantages of the remaining biasing techniques. Next, we're going to learn about the stability, temperature dependence parameters of BJT. The next session we are going to do that. Okay. Is it clear, everybody? Now we're going to write the test. So let you wanted to revise this simple brief revision. Yes, I'll start it.